class, today we are doing a video on factoring polynomials. So this is quite a important video for you guys to understand, and we're going to be doing quite a lot in it. So I hope that you are ready to go. Okay, so you can see what the learning goals are here. We're going to be talking about the remainder theorem and the factor theorem, learning what they are, and also learning how to factor. So we start with just a reminder of what a factor is. So if I ask you with numbers, what are the factors of 12? So the factors of 12 are any numbers that divide evenly into 12. So 1, 2, 3, 4, 6, and 12 are all factors of 12. So that means that if you did 12 divided by any of those numbers, you wouldn't get a remainder. So the same is true when we move to polynomials. So a polynomial is a factor of another polynomial if, when divided, the remainder is 0. Okay, so that's kind of where we start with that understanding. So if something is a factor, the remainder will be 0. So in this question, 2x plus 3 is one of the factors of this polynomial. Determine the other factors. Well, since it is a factor, we know that when we do synthetic division, we will get a remainder of 0. So watch what happens. So we do our synthetic division. Okay, and remember we're dividing by minus 3 over 2. Okay, since 2x plus 3, the x-intercept of that would be minus 3 over 2. So, oops, I'm having a bit of trouble with my technology today, but hopefully we can make it through this now. Okay. So, we bring down the 6. Okay, and then we multiply through. So we get minus 9, which gives us minus 4. Then we get minus 10. Sorry, this should be minus 3 over 2 up here. Sorry, that's a 6. So that adds to minus 10. And this times that gives us 15, so 0. Okay, so we get this result here that x minus 3 over 2 times 6x squared minus 4x minus 10, and then you have a 0 remainder. So that is another way of writing out this polynomial. So remember that we don't want x minus 3 over 2 here. We want it to be, sorry, it should be plus. We want it to be 2x plus 3. So in order for that to happen, we want to borrow a 2 from here and move it over there. So then we get your 2x plus 3, which is what we want. And then we divided a 2 out, so 3x squared minus 2x minus 5. So now this is just a complex trinomial. Okay, it's quadratic, so this is back to grade 10. So if you factor that using decomposition, you would get 3x minus 5 times x plus 1. If you need a refresher on that, go ahead to look back in your grade 11 videos or notes on how to decompose that. So that means that 2x plus 3, 3x minus 5, and x plus 1 all divide evenly into this big polynomial. So that means if you were to do synthetic division with any of these 3 brackets, you would get 0 as the remainder. Okay? So those are the 3 factors. Okay, so this little communication note area, this is getting us into understanding what the factor and the remainder theorem are. So remember from yesterday that if we have a polynomial, p at x, it can be written as the quotient, so q at x, times x minus b, right, that divisor, plus the remainder, okay? We also learned that if you wrote it this way, it would be p at x over x minus b equals the quotient plus the remainder divided by x minus b, okay? So q is the quotient, and r is the remainder. Sorry about that, the remainder. Okay, so how does this help us to determine if a polynomial is factorable? Well, this example isn't going to make sense to you right off the top, but just bear with me, okay? So just watch, you might just want to watch what I'm doing and then copy it down. So if I let my p at x be equal to this polynomial, so 2x cubed plus x squared minus 3x minus 6, okay? And I want to divide it by x plus 1, okay? So watch what happens when I use my definition above. So p at x equals q at x times x plus 1, because that's what I'm dividing by, plus my remainder. So I'm going to put minus 1 in for x. Now, where am I getting the minus 1 from? Well, because when you set x plus 1 equal to 0, you get a minus 1. So I'm putting in a minus 1 for x. So p at minus 1 means that we're going to have q at minus 1 times minus 1 plus 1 plus the remainder. So check out what's going on here. This means that you get the quotient, whatever it is, it's some polynomial. But look what happens here. Because I'm putting in minus 1, which is the number that makes this bracket 0, that makes this whole part equal to 0. So I actually just get that p at minus 1 is equal to the remainder. So when I'm dividing by minus 1, if I put that value into my function, that will tell me what the remainder is. So in this case, p at minus 1 is negative 4. So if you put minus 1 into this function, blah, 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 you get 4. So that means that if you do this division, you'll get a remainder of minus 4. That's kind of interesting. So let's try it again with a different example. What about if you do this division? Well, again, if we let p at x be equal to this, okay, so let's let this be p at x. Okay, and then we're going to put x equals, x equals minus 2/3 in and see what happens. Okay, so we get p at x equals our quotient times 3x plus 2, and then plus the remainder. So remember, that's just a way of writing the solution. So what happens when I put in minus 2/3? P at minus 2/3 gives me my quotient at minus 2/3, and then 3 times minus 2/3 plus 2 plus my remainder. Well, again, this section goes to 0, so this whole front section goes to 0. So I get p at minus 2/3 is my remainder. Okay, so that's kind of exciting. So that means whatever the function is equal to when I put in negative 2/3, that's the same number as the remainder when I divide by that. Okay, so that leads us to the remainder theorem. So it turns out that that little result works no matter what. So that leads us to this actual theorem. So a theorem is when something is always true. So when a polynomial is divided by ax minus b, the remainder is equal to f at b over a. Okay? When I say f at b over a, you can think about whatever makes it 0. By it, I mean that. Okay? So for example, if I'm dividing this polynomial by x minus 3, and if all I care about is the remainder, all I have to do is find f at 3 to find what the remainder is. So f at 3 is 14. So therefore, the remainder of that division would just be 14. So why is that good? That's good because then that tells us if we get a result of 0, then that means that something is a factor. Because if the remainder is 0, then that means that division gives you a perfect factor. So ax minus b is a factor of f at x if and only if, when you put b over a, so f at b over a, in, you get 0. Okay, so therefore, factors of the form ax minus b must have a b value which divides into the constant term. Okay, so factors of the form ax minus b which have a b value which divides into the constant term. So I'll show you what that means here. So for example, if you have this, okay, this is going to give us 3 factors when we divide it, if it's perfectly factorable, okay? So it's going to give us x minus a b1. That's our first 0. X minus a b2. And x minus a b3. Okay? So therefore, when you actually expand this out, to get a constant of 24 at the end here, when you multiply the b1 times the b2 times the b3, you would have to get 24. Okay? So therefore, b1, b2, and b3 must be factors of 24. So that's what that means, that the factors have to have a b value, so this last value, which divides into the constant term. So for this example here, we're going to factor this, okay? So the only way to factor, unfortunately, here's where I lose you, is by trial and error, okay? That's the only way that we know how to factor these things. So basically, we just have to pick what we think might be factors and just start trying things until we get a remainder of 0. So that's why it's important to understand. See, the a value here is just 1. And our constant term out on the end is -6. So that means that all the possible factors have to be divisible into -6. So we don't want to just start trying anything. Our possible factors are just what are divisible by -6, or what -6 is divisible by. So plus or minus 1 could work. Plus or minus 2, that goes into 6. Plus or minus 3, that goes into 6. Not 4, not 5, plus or minus 6 also goes into 6. So there's going to be 3 different factors out of 1, 2, 3, 4, 5, 6, 7, 8 possibilities. So we just need to start trying things to see when we get a remainder of 0. Okay, so that's the sucky part about this, is that there is trial and error involved. So there's 2 different ways of doing this. Number 1 is just to test the function b, where b is one of these possible numbers, until you get that f at b is equal to 0. Because when you put it in, if you get 0, because of the factor theorem, that means the remainder is 0, which means it's a factor. So for instance, I can test, I'll give you a hint, 2 is one of the factors. So if I put f at 2 in here, I would get 2 cubed plus 2 times 2 squared minus 5 times 2 minus 6. Okay, so that's 8 plus 2 squared is 4, so 8 minus 10 minus 6, which gives me 0. So that means that x minus 2 is a factor since I got a result of 0. Okay, the other way of doing this is to just go right to synthetic division. And this is the way that I personally prefer, is I just make my little synthetic division table. I know I'm going to have 1, 2, minus 5, and minus 6 up here. And I just start testing numbers on the outside here until I get one that gives me a result of 0 down here. So I know I need a 0 here. Okay, so now I just start testing. So I start with 1 to see if that works. Okay, so I bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 3 times 1 is 3. Minus 5. Plus 3 is minus 2. And then that gives me minus 2. And I'm not going to get a remainder of 0. So 1 doesn't work. That sucks. So erase, 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 erase. Okay, so now I'm going to try 2. Because 1 didn't work. So 1 times 2 is 2. 2 plus 2 is 4. 4 times 2 is 8. Add that, I get 3. 2 times 3 is 6. Woohoo! That actually did work. So that means I can go right to x minus 2, x squared plus 4x plus 3. Okay? And now, this is just a quadratic, so I can factor it using my normal quadratic methods. So it multiplies to 3 and adds to 4. So I just go right to x plus 1, x plus 3. So there you go. Those are my factors. So this is my final answer. This is the fully factored version of what I did above. Okay? So that means if I had put in 2, minus 1, or minus 3 in for my synthetic division, I would get a remainder of 0. Or if I put 2, minus 1, or minus 3 into the function here, I would also get a result of 0. Okay? That also makes sense because these factors are just the x-intercepts, so that should give you a result of 0. You can think about what that would look like graphically. It would be the x-intercepts. Okay? So the big bummer in all of this is that you have to do trial and error. But it's smart trial and error, okay? There's only certain things that you want to try. So if f of x is a polynomial with integer coefficients, okay, and x equals b over a is a 0, so in other words, ax minus b is a factor, then b, so the numbers you test for b have to be factors of the constant term of p at x, so the thing that you're dividing, and a have to be factors of the leading coefficient of p at x. Okay? So you always want to check your integer factor first and then your rational. So this is because, okay, for the proof of this, if you have your ax or a1x minus b1 times a2x minus b2, a3x minus b3, all the way, however many factors you have, to anx minus bn. Think about when you actually multiply this all through to get your coefficient, that the a's, a1x, or a1, sorry, times a2 times a3 times an have to give you the leading coefficient, right? Because you'll multiply these all through first, and so that is leading coefficient. So that's why they have to be factors of the leading coefficient, and I already showed you in the previous page why the b's have to be factors of the constant. Okay, so when you are testing your factors, they're the form b over a, where b is factors of constant, and a is factors of the coefficient. Sorry, leading coefficient. Okay, so that just kind of tells you what you're supposed to test. But that being said, don't test fractions unless you have to. Normally, on most of these homework questions and on the test, there will be at least one integer factor, and then you could find the fractions later when you factor the quadratic, which is much simpler. So, like for instance, this one, to think about all the possible factors, you start with the constant, okay? So your possible factors here are plus or minus 1 and plus or minus 2, okay? But then, because those are factors of 2, well, we also have any fractions that are plus or minus factors of this guy divided by factors of this guy. So plus or minus 1 over 3 or plus or minus 2 over 3. So factors of this guy divided by factors of this guy. Okay? So I don't need to show over 1 because that's already included here. So when I'm starting out my synthetic division, please try plus 1, minus 1, and plus 2, minus 2 before you start trying fractions. And I almost guarantee you that you'll always be able to find one integer, okay, that will divide in. So I set up 3, 2, minus 7, and 2. Okay, and remember I'm trying to get a remainder of 0 here. So now I just need to go through and test. So I try 1. Okay, I'm going to try 1 first. I'm just hoping I'm lucky. So I'm bringing down my 3. 3 times 1 is 3. You add these together, you get 5. 5 times 1 is 5. Add these together, you get minus 2. Yay! I got lucky. So that means that x minus 1, right? You have to do minus 1. And 3x squared plus 5x minus 2 is a factorization of this. But I can factor this further because it's a quadratic into x plus 2 and 3x minus 1. So notice if I had put in negative 2, that would have worked as well, or 1 over 3 would have worked as well. But there's my final answer. Okay? So now let's try example 4. Okay? So another method is to factor by grouping. So factoring by grouping means that you take the first 2 terms and the second 2 terms and group them, okay, and do some common factoring. This doesn't always work, but it's worth taking a look because it is quite a bit simpler. We actually already did this kind of factoring in grade 10. So you can take out an x squared, and you're left with an x plus 2. And here you can take out a minus 9, and you're left with an x plus 2. So you know this works because you get the same factor here. So you can take out a common factor of x plus 2, and you're left with x squared minus 9. Now x squared minus 9 is a difference of squares, so you're left with x plus 2, x plus 3, and x minus 3. Okay, you still could have done this question using synthetic division and the guess and check method, and you would have gotten the same answer, but this is just a quicker way if you're able to see that that's a possibility. Okay, example 5, try factoring this by grouping. Okay, so again, my first 2 and my last 2. So I can take out an x3 of the first 2, and then I'm left with x minus 6, plus a 2x, I'm left with x minus 6. So then I have x cubed plus 2x times x minus 6. And this has a common factor of x, so I can take that out. And I know I'm done factoring now because there's nothing else I can do. I took this x out. There's no common factor here, and there's nothing else for me to factor, so I'm done. So you can only be done the factoring when you know that's all done. Okay. Here's a question that is not a factoring question, but it uses your knowledge of the remainder theorem and the factor theorem to solve a problem. Okay? So here we have this polynomial here. Why is this doing this? Okay, is being divided by x plus 1, and the remainder is minus 12. Actually, you know what? I'm having a bit of trouble with my program right now, so I'm going to stop this video. Actually, it's a fine time to stop because now you've seen all these examples of factoring. So please scroll down and do those practice questions, okay? The factoring. For the sketching question, what you need to do is factor it, and then that will give you the zeros, okay? And then you're able to draw a possible sketch using those zeros, okay? So I will do example 6 on another video, as well as factoring a sum or difference of cubes. Okay, thanks for watching. Hope you learned lots.